All right, I think we've got this kind of working now. So today we're going to be quickly reviewing how we use abbreviated truth tables to test for the validity or invalidity of arguments. And just a reminder, the theory behind abbreviated truth tables is that we don't need a complete truth table. We just need one row of that truth table, just one, to show that there's one row where all the premises are true and the conclusion is false. This would show that the argument is in fact invalid. And if we cannot construct such a row, it would show that the argument is valid, right? So if we cannot do this, we show validity. If we can do this, we show invalidity. So that's the theory behind truth tables. But now let's put one together and see if we can construct it. I'm going to change the color of this pencil here because I don't really like red. All right, so let's just work through the steps together as we construct an abbreviated truth table. So step one is to hypothesize that the premises are true and the conclusion is false. And what that means is we're going to go up here to this part of our truth table and just assume that all the premises are true. And we're going to assign that truth value underneath the main logical operator of each of the premises. So here's a premise, and here is a premise, and here is a premise. And I assign a truth value underneath the main logical operator. And then, so I say, okay, all the premises are true and the conclusion is false. So under the main logical operator of the conclusion, I say, well, that is false. Okay, so let's erase all of these extraneous marks. Okay, and let's come back to do step two. So step two is to determine the truth value of the atomic statements of the conclusion. Remember that. That satisfies the hypothesis. So what does that mean? It means we're going to start by looking at C dot D. That's our conclusion. And we want to know what assignment of truth values of C and D will yield a truth value assignment of dot as false. Remember, dot is the main logical operator. Also, that's tricky because C dot D is going to be false under most truth value combinations of C and D. The only time dot is true is when C is true and D is true. So we may have to construct multiple rows here in order to see if our hypothesis is correct. So let's, just getting some dust off. Let us start by just guessing. So let's say C is true and D is false. And that will make dot false. So that is step two. Step three, follow through with uniform truth value assignments of the atomic statement. So what does that mean? Well, it says, look, we gave a truth value to C and we gave a truth value to D. And that satisfies the hypothesis that dot is false. And now what we do is we go back into the truth table, and whenever we see a C, we give it a truth value of true, and whenever we see a D, we give it a truth value of false. To go here, here's a D, it's false. Here's a C, let's call that true. And that's as far as I can get right now. And so the rest of what we have to do is work from the premises. So we're going to go over to the premises and see if we can now figure out what their truth values are going to be. This is still step three. So here's a situation. So let's look at tilde B, arrow D. We said that arrow has to be true. That's the main logical operator of this premise. The consequent of that conditional is false, but arrow is true, which means that tilde B, which is the entire antecedent, cannot be true. Tilde B must be false. And if you're wondering why that has to be the case, it's because arrow would be false if tilde b were true and d was false. So in order for arrow to be true, tilde b must be false. If tilde b is false, then b itself is true. So that gives us a truth value assignment for b. Here's b over here, so we're going to say b is true. So now let's work on this premise because we can do some work here now. So if tilde a dot b is true, then a dot b itself must be, this dot has to be false. If b is true, though, for dot to be false, a cannot be true, otherwise dot would be true. So a must be false. Good, so that gives us a way to go over here and think about this. So we said this a has to be false. So tilde a is true. So if tilde a is true and c is true, arrow is true. So that checks out. So what we've done is now we have, we're at step 4, we have confirmed our hypothesis. There is a uniform assignment of truth values where all the premises are true and the conclusion is false. And how do we know that? Because we just made it. Get rid of some of this extraneous stuff. And now we're going to fill in the rest of our truth table. Right, so uniformly assign those truth values on the left side of the truth table. And that's only do that if it's confirmed. So here's what we said. When A is false, and B is true, and C is true, and D is false, this line right here shows that the argument is invalid. And abbreviated truth tables are really the best way of testing for invalidity. Let's do another one. Oh, sorry, if I moved off of that too fast. There you go. Take a look at that. Let's take a look at another one and just work through it together. So again, step 1, hypothesize that the premises are true and the conclusion is false. So here we go. We're saying that arrow is true. That arrow is true. H is just by itself is true, and tilde D is false. Remember, that's under the tilde. And we're saying if tilde D is false, then D itself is true. So step 2, uniform assignments of the atomic statements. Well, I guess we're on step 3, that satisfy the hypothesis. So D is true. Here H is also true. We know that. And now let's figure out what we can do with this. Let's start here. So when D is true and arrow is true, B must be true. So that helps. It must be true. We have another situation here. H is true and arrow is true. So tilde B must be true, but we already said that B is true, which means that tilde B is false. But here's what we're then saying. We're saying that when H is true and tilde B is false, the arrow itself can be true? Well, look, we know that's not right. And so what we've done, I'm going to get rid of this, is we've shown that there's no way to confirm our hypothesis because there's no uniform assignment of truth values of H, B, and D that will yield that row of the truth table that we were looking for. When we can't do that, we put that slash. That slash has to occur under a logical operator. We have to say, here's the logical operator that we can't get to work with the assumptions that we've made. So this abbreviated truth table shows that the argument is valid. There is no such row where all the premises are true and the conclusion is false. And therefore, it is a valid argument. Let's just do one more real quick. Confirm or make the hypothesis that all the premises are true while the conclusion is false. Since there's only one truth condition under which arrow is false, it's when the consequent is false, but the antecedent is true. We know the truth values for W and Y. So tilde W has to be true, so W itself must be false, and Y must be false. So now we'll come over here to the premises. W is false. Let's see, and Y is false. And that's as far as we can get right now. This is helpful because arrow is true, but Y is false, which means tilde Z has to be false. And Z has to be true. I'm kind of rushing here because I don't want to make this too long. But if you don't know why, consult your the truth tables for our logical operators. So Z has to be true, so we'll come over here. Z is true. We know that this has to be false if this is true, so let's go ahead and make that false, which means H has to be false. We're going to come back over here now. Here's another H. Say that H is false. When W is false and H is false, is arrow true? Yep, that checks out. So we have confirmed our hypothesis that when Z is true and H is false and Y is false and W is false, that we produce that one row that shows that the argument is invalid.